Or actually, see you tomorrow.
Oh yeah, see you tomorrow.
I have two questions about the cardiovascular.
Oh sure.
project.
Yeah.
So
Nice. That's great.
this counts as A, right?
Yes. And so as long as there's 8 paths and 8 segmentations, that's it.
Okay.
Yeah.
And
Mhm.
second question, for the model, do you want, like, for my specific project,
Mhm.
would you prefer like different models?
There should just be one model. So
Just
the one
one
model,
model?
the one model should have all 8 vessels together.
Okay, because I made like a separate one, like one like for
Uh-huh.
the right side and the left.
Uh-huh.
And I just composed both of them.
Yeah. So there should just be one. And so
Just
it should
one?
have you should have all 8 vessels together. Because what we're gonna do, I think in a
Doing
few weeks is that
mesh?
yeah, so we're gonna mesh all this together as one, and then we're gonna run a simulation on just that.
Okay,
Yeah, it looks great. That's perfect.
thank you.
Yep. Mhm.
Thank you, Matt.
No problem. See you guys.
You played Elden Ring?
I have not, but I've seen a lot of videos of it. It looks really fun.
It is. I don't have a system, but my friend got the new Xbox,
Mhm.
and so he got it. And so one weekend I go over and I'm like, dude, have you heard of this new game Elden Ring? I'm seeing like everybody post about it.
Mhm.
And he's like, yeah, dude, I got it a couple weeks ago or like last week. You want to try it?
Uh-huh.
And I was like, fuck yeah, I want to try, right? It's
Uh-huh.
like I had always heard how hard these From Software games are.
Yeah.
And I swear to God, I spent like, it took me probably 30 minutes or an hour just to get through the catacomb that we were in, like just fighting the small enemies, right? So I learned how to beat the small enemies.
Uh-huh.
And then I was fighting a minor boss.
Uh-huh.
It probably took me like, I want to say 2 hours or 3 hours to beat. And so, you know, I go over there on the weekends and I play sometimes. And like this past weekend, I was fighting the same boss
Uh-huh.
from like probably like 5:30 in the afternoon
Uh-huh.
till 2:30 at night. I finally won.
Wow.
So I mean, it's really fun though. Like your character is super customizable
Uh-huh.
in terms of the way you can make it look,
Yeah.
and your stats, like it's super customizable too.
Nice.
So it's pretty cool. Definitely, I would recommend trying, but probably not during the school year. It is addictive for sure. Like, I'm lucky I don't have a system, because if I did, like, I would get no work done whatsoever. Like, the world is so big and explorable, you could just spend hours playing.
Yeah, I've heard so many great things about it. I'm thinking maybe over summer I might try to pick it up.
Yeah, it is. It's good. It's definitely worth the pickup. And by then too, you could probably play through the main story and then DLC will probably be on its way after that too.
Nice, nice.
Because I'm assuming they'll probably do DLC within like 6 months or a year, I would imagine.
They usually do. Yeah.
So, yeah, that would be cool and fun.
Nice, nice.
Hey, Justin,
Yep. What's up?
I have a question about the homework.
Uh-huh.
About two B, two C,
You see?
I think so.
Let me take a look.
I think.
To see.
Two C.
Ah, uh-huh.
You're supposed to give us the thermal conductivity.
Thermal conductivity. It should be the same as 2A. Oh, did I give it here? Oh, I don't. Okay. Oh, it is. It is. It's right here. So what I say is the K is constant and it's 600.
But that's a different.
Yeah, 2C is to repeat problem 2A. The only difference is that because I think 2A we don't have an S, and so we say S is 0 here. And then for 2C, it's the same, exact same parameters, but now you have an S is 10 cosine. Yeah.
All right.
Mhm.
Never mind.
Mhm. Hey, how's it going?
How was your break?
Huh?
Taking a break.
Yeah. I mean, I didn't have to lecture or talk to any of the admins here, so that's always a break. But I just caught up with grading and did a bit of research. So I always tell people the best parts of my job here is when I get to be with students, number one, and number two is when I don't have to talk to anybody else. That's the best parts of this job. So. Hey, how's it going? All right, it's 7 o'clock, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? How's everyone's spring break? Good, good. Yeah, so I apologize for assigning homework over spring break. I know, you know, that's usually not a good thing, but it's just kind of the way the timing of the class was that, you know, I kind of had to do that just so that, you know, we can kind of stay on track. The last time I taught this class was actually in the fall semester. And so, you know, if you know fall semester, spring semester, the timing of the break is a bit different. And so we're gonna have an awkward pause kind of, I think, week 13, week 14, where that's where fall recess used to be. Or I mean, still there, but you know, it's not here in spring semester. So that's why things kind of was kind of timed a bit awkwardly. So you know, but the homework's gonna be due next Monday. And so you guys still have one more week to get it done. Okay. So the plan for today is we have kind of a hybrid day today. And so I have a bit more notes to finish up on Gauss Quadrature. And so I want to make sure I finish that. And then we're gonna have another MATLAB day. And so it's time to, you know, we spent a lot of time in the previous unit talking about how to implement direct stiffness problems in MATLAB. We're gonna jump right back into it here. And so, you know, we've learned how to do the finite element method for differential equations in 1D. And so we're gonna see how that's implemented in MATLAB. Okay. And so from here on out, you know, the MATLAB is going to be, you know, it's going to be a little bit heavier focus of the class. I think I'll talk about, you know, the final project. I think it'll make sense to talk about it next week after we, you know, after we've seen kind of the 1D finite element solver, because after that, then the final project will probably make a lot more sense. Okay. All right. And so I think that's it for my announcements. So are there any questions I can answer before we get started? Yep.
Is it gonna be the same thing as your other classes where you make it do like a tiny bit after finals?
Yes. Yeah. Yeah. So I think the date for this semester is going to be May 23rd. So I think finals week is the previous week, and then Monday the 23rd is going to be when it's due. If you're graduating this semester, apparently the 23rd is graduation day, and so you know, if you still need to finish it up after you walk, then you can do that. But I didn't know that was the case. But I'll be at graduation, and so if you have questions on the project and you see me at graduation, you can just kind of pull me to the side and ask me something, and I can answer you. Okay. Yeah, just bring the laptop. I'll be. Yeah, we'll do it as we're walking up, because my job for the graduation is to help usher, you know, people up to the stage. And so yeah, we'll just walk together. I'll decode your MATLAB as we're getting on stage, and then you can shake Dean Brewer's hand. I'll hold on to your laptop. So you can shake Dean Brewer's hand, come back, and then I'll give you your MATLAB. All right, any other questions before we get started? Okay, so let's go ahead and pick up where we left off. All right, and we were talking about this technique last time called Gauss Quadrature. Okay. And so Gauss Quadrature is what it is it's a technique for evaluating integrals numerically. Because normally when you evaluate an integral, right, you have an integral, you take whatever the integrand is and you find its antiderivative, and then you apply the bounds on that antiderivative. And so a lot of times, that's either not possible or it's just really, really inconvenient. And so Gauss quadrature is one of many techniques that are out there to take that takes an integral and evaluates it without having to perform that antiderivative. Okay. And so the idea is the following. And so if you have an integral here, right? And so here's our integral of f of x dx. Instead, normally what you would do is you would take f and you would find big F of x, where big F of x is its antiderivative, okay? And then apply the bounds on that. Sometimes that's just not possible, or it's just really annoying to do. So what you can do instead is you can replace this with a weighted sum and so you take the integrand itself, and so the function f of x you already know, and so plugging a value of x in there is trivial, okay? And you can have as many terms as you want, although for most practical cases you only have one or maybe two terms in your Gauss quadrature, okay? And so at the end of class, I think at the end of class before the break, someone asked me how this compares to Riemann sums. And so Riemann sums is probably another technique you've learned in your calculus classes long, long ago. And so this is very similar to Riemann sums, except Gauss quadrature has a little bit better convergence criteria. And so you get a more accurate solution with Gauss quadrature for less amount of work than Riemann sums. Okay. But both are great. Both are great methods. And if you take more classes and numerical methods, you'll learn more methods as well. You'll learn trapezoidal rule, Simpson's rule. They're all good. But Gauss quadrature has the best it converges a lot faster. Okay. All right. So I believe last time we learned how to apply this in kind of a simple case, okay? Because the caveat or the catch with Gauss quadrature is that you can only apply it when the integration bounds go from -1 to 1. Okay. Because remember last time we talked about the Gauss points and the Gauss weights, right? But that only works if your integration bounds are -1 to 1, okay? Which seems very limiting because the amount of integrals out there that don't go from -1 to 1 is infinitely many, right? And so in order to deal with these situations, what we have to do is we have to perform what's called a change of coordinates. Okay. Okay. And so that transformation mathematically looks like the following. So we have a generic integral here. And so we have integral from x1 to x2 of f of x dx. Okay. We can transform this. And so if we have our integral here, right, instead of x1, x2, where x1, x2 can be almost anything, and then we transform it to -1 to 1. The key to doing this is a transformation. And so instead of integrating over x, we integrate over this new variable called epsilon, okay? Or at least I think it's an epsilon. My Greek alphabet is pretty awful. Okay? And so that's our change of coordinates. And so instead of integrating over x, we integrate over this new variable. But this new variable is related to x. Okay? Okay. And so our function f here, it's still going to be a function of x, but now x is going to be a function of this new variable. Okay, and so it's kind of like an inception kind of thing. Like you have to kind of go one step deeper than the surface. Okay, and then we also have this new factor here. Okay, we call it dx d epsilon. Okay, and this factor here, you can almost think of it as like an additional conversion factor. And if you kind of want more details of this conversion factor, it has to do with the fact that a lot of times when we perform this change of coordinates, the size of our domain is going to change. Okay. And the name of this conversion factor is called the Jacobian. Because a lot of times when you perform a change of coordinates, let's say that you have an integral that goes from, I don't know, 0 to 25, right? And so the length of that domain is 25, right? So you go from 0 to 25. But if you're going to transform that integral into an integral between -1 and 1, the distance between -1 and 1 is only 2. And so if you're going to go from a domain of length 25, you shrink that down to a domain of length 2, then there has to be a factor there that accounts for that compression. So that's what the Jacobian does. Okay. I think that's easiest to interpret in 1D, because in 2D we're going to have the Jacobian again, but it's going to be a lot more difficult to interpret. So I want to make sure I discuss it here, just to kind of just so that you kind of know what it means and what it represents, so that when we go to 2D, you kind of have that intuition going in. But that's basically what the Jacobian is. Okay. Okay. And so next, what we're going to do is we're going to go through we're going to go through the mechanics. We're going to go through the process of how do you actually perform this change of coordinates, so that you can actually start to apply it for your finite element problems. All right. Any questions on this? Okay. All right. And so let's go ahead and walk through how do we actually perform this change of coordinates. Okay. And so we need two things to perform our change of coordinates. Okay. And so the first thing that we need is x of epsilon. Okay. And so what this is, you can think of this as another function. And so this function here, what this does is that it maps the physical coordinate onto the Gauss coordinate. Okay. Which sounds very opaque and sounds very mathy, but you'll see it's not that bad. And so we're going to use the shape functions to kind of help us out with this. Okay. All right, and the other thing, of course, is our Jacobian. So we need dx d phi. But once we have number 1, computing number 2 is very easy. And so all we have to do is just simply take the derivative to get number 2. Okay. And so what I want to focus on is how do we obtain x of phi. Okay. All right. Right, so here's where we do a little bit of blending. And so, up to this point, Gauss Quadrature is kind of a general technique for numerical integration. And so it exists outside of finite elements, although finite elements is one of its greatest customers. Okay. Here we're going to start to blend the two together. And so, there's a lot of how we set up the finite element problem that actually makes it convenient to do Gauss Quadrature. And that's kind of why the two kind of go hand in hand. Okay. And so the way that we're going to obtain x of epsilon here is we're going to use our finite element shape functions. Okay. Because remember, so remember what the purpose of the shape functions are. So here we have a typical 1D element. Okay. Right. And so our shape functions, remember, were n1 and n2, right? Okay. So they're functions of x, right? And so before, what we did, the purpose of the shape functions was to help us interpolate our solution to any location within the element. Okay. And so the idea with the shape functions is that we have the nodal solutions, right? And so we have use t actually. Okay. And so we have t1. Remember, t1 is the solution of our function at node 1 here. Okay. And we have t2. Okay. And our physical coordinate here is x. And so if we wanted to find t at any other location in the elements, we have t of x. What we can do is we can say this is equal to t1 n1 of x, okay, plus t2, n1 of x times t2 n2 of x, right? Right. That was the basis of our shape functions, and then based on this, we were able to obtain our element stiffness matrix and element forcing vector and all that good stuff. Okay, let's use that same idea, okay, and apply that to Gauss quadrature, okay? Because remember, in Gauss quadrature, we're making a change, okay? And so this is our Gauss domain. It's our Gauss domain. Right? Our Gauss domain, instead of being x1, x2, is going to be instead epsilon1 is equal to -1 to epsilon2 is equal to +1. Okay. And so instead of n1 of x, what we have is n1 of epsilon. Okay. And we can also have n2 of epsilon as well. Okay. And so we can use these shape functions to kind of interpolate anywhere within this domain. Okay. And in fact, let's go ahead and write out our expressions for n1. Okay. So even though the variable is different, we have epsilon here. Our shape functions still have the same expression. So remember, n1 of epsilon is equal to epsilon minus epsilon2 divided by epsilon1 minus epsilon2. Okay. So let's go ahead and plug into this expression here. So epsilon2 here is 1. Okay. Epsilon1 here is -1. Right. And so if we work through the algebra here, we have a -1/2. Okay. Which I'm just going to factor out as just 1/2. And then the numerator here is going to flip sign. So we have a 1 minus epsilon. Okay. And similarly, n2 is epsilon1 minus epsilon divided by epsilon1 minus epsilon2. Okay. All right. And so if we plug in for this, and so we have epsilon1 here is -1. Okay. And epsilon2 here is 1. Okay. And so we have a -1/2 multiplied by -1 minus epsilon. So we have a 1/2, 1 plus epsilon. Okay. And so those are the functional values, or so those are the functional expressions of our shape functions in this very kind of specialized case. Okay. Right. And so all I've done so far is I've taken our usual expressions for the shape functions, right? And so this n1, n2, those are the generic those are the generic expressions for the shape functions. Although instead of x here, I've used epsilon, and I've plugged in the actual values here. So since we already know what epsilon1, epsilon2 are, we can go ahead and plug those into our, to our expressions here. Okay. All right. Any questions on what I've done so far here? Okay. All right, so let's look back up here and see, how we use these shape functions. And so, for the normal case, for the finite element case, we used our shape functions to say that, if we have T1 defined at node 1 and T2 defined at node 2, then what this does is that it allows us to find a function of T for T as a function of X, right? Right. Here instead, what we have is, instead of our physical coordinate being X, our physical coordinate is epsilon. Okay, and so if we have like T1 here and T2, right, what we can have is T of epsilon is equal to T1 N1 of epsilon, okay, plus T2 N2 of epsilon. And so the exact same thing, except instead of X, we have this kind of specialized Gauss coordinate instead, epsilon. Okay. Okay. But we aren't just limited to T's here, right? So the only requirement to use this interpolation, let me write down here, okay? The only requirement for this interpolation is that our quantities here, T1 and T2, they have to be defined at the nodes. Okay? Okay. And so they don't necessarily have to be the solution to a finite element problem. They can be used to represent anything that that occurs at the nodes. Okay. Okay. And so let me go ahead and erase this T, although I'll leave the rest of the skeleton there. Okay. And let's think about what else do we know that are defined at these nodes as well, right? And so besides T, what other properties do these nodes have? Right? Right? These nodes also know what their physical coordinate is, right? So the other thing that are defined at these nodes is just the physical locations of these nodes. Okay? And so what we can do is that instead of T1, T2, we can just replace them with X1, X2, right? And then that turns our function here, instead of T of epsilon, instead what we have is X of epsilon. Okay? And so we have X of epsilon is equal to X1, N1 plus X2, N2, where N1, N2 are these functions of epsilon right here. It's a little bit hard to kind of get your mind around, because when we first defined these shape functions, the X was the actual coordinate that we're using for the interpolation, right? But for Gauss quadrature, we're not using X for the interpolation anymore. We're using epsilon for the interpolation. And instead, the X is being used as the subject of the interpolation. So the X is actually what we're interpolating on this function here. And so it's a little bit, it's a little bit of a, it's a little bit kind of a circular reasoning, but once you kind of wrap your head around it, it becomes a bit obvious. And then through that, we're able to obtain the exact thing that we're searching for, right? So remember we started this journey saying that we need this function X of epsilon, right? We have no idea what it looks like yet, Okay, but we need it in order to perform our change of coordinates. Right? Through the use of our shape functions, we're able to obtain just that. Right? And so this shape, this functional representation here is simply just, you know, the physical coordinates of each node multiplied by these more specialized shape functions. Okay. So this is one of those things where, you know, we have kind of incredible synergy between, you know, two, you know, I mean, related, but not, you know, they weren't developed together. Two different things that kind of work together in a very beautiful harmony. And this isn't the last time that we'll see this too. So once we start talking about 2D finite elements, you know, we're going to leverage the same thing, because in 2D finite elements, you know, in 1D, it doesn't really have a special name. We just call it change of coordinates. But when we apply the same methodology in 2D, it's called isoparametric elements. And so isoparametric elements is I think it's one of the most central concepts to, you know, a lot of modern day finite element codes. And so, you know, this idea of, you know, taking those same shape functions and using them to represent the coordinates is very central, very key to that concept. And, you know, and so we'll be revisiting this a lot, you know, for the rest of the class. Okay, any questions on this? Okay. All right, and so now that we have this this function right here, that's part one of what we need. And so the other thing that we need here is the Jacobian. Okay, but the Jacobian from this is very simple, because all we have to do is just simply take the derivative. So the Jacobian is dx d epsilon. Okay. And so we take the derivative of this. X1, x2 here are just constants because those are the physical coordinates of the nodes. And so we have x1 here. Okay. N1 is a function of epsilon, and so we can take the derivative of that. Okay. Same thing with N2. So N2 is also a function of epsilon. Okay. All right. And so, you know, normally when we take derivatives of shape functions, we kind of leave it like this. But because we have a specialized value of these shape functions, we can actually take this a bit further. Okay. And so, for instance, let's plug in N1 here. And so if we take the derivative of this guy with respect to epsilon, right? Okay. The 1/2 is going to go away because it's a constant, and then all we're left with is a minus epsilon over 2. And so the derivative for that is minus 1/2. Okay. And then similarly for N2, we take the derivative, and then we end up with a positive 1/2 for that guy. Okay. And so let's go ahead and plug that in. And so we have a minus x1 divided by 2 plus x2 divided by 2. And so we kind of simplify this a bit. We get 1/2 x2 minus x1. Okay. All right. And so remember I mentioned before that the Jacobian in 1D is basically a factor that accounts for the fact that our domain size might be shrinking. Okay. And so one way that you can, the one way that you can view this is that in the numerator here, we have x2 minus x1. And so you can think of this as kind of the size of our original integration domain. Right? Because we're integrating from x1 to x2. And so that's the amount of distance that we're going to cover. Okay. And this 2 in the denominator here, this is the size of our Gauss domain. Okay. Okay? Because remember, we're integrating from -1 to 1, and so the size of that domain is 2, right? The distance that you cover is from -1 to 1 is just 2. And so the way that you can interpret this Jacobian is that it's a ratio. It's a ratio of, you know, how big your integration domain used to be divided by how big your integration domain is now. Okay. And so that factor is important to make sure that your new integral is scaled correctly. Okay, any questions on this? All right, so let's do an example to see how all this works in action. And so I believe this example is taken from the last finite element problem we did before the break. And so we want to evaluate this integral. Okay, and so our integral here is 200 integral from 0 to 5 of 1 plus x squared divided by 400 dx. Okay. And we want to do this using a, how many points? And so we want to do this using a 2-point Gauss rule. All right. And so we already know what this integral answer is. And so if you look back in your notes to the last finite element problem, you know that you'll see that when we evaluated this integral exactly, or through the antiderivative, we got, so the answer for this integral is 1020.3. Okay. And so let's see if we can obtain that same result through a 2-point Gauss rule. Okay. And so first thing we notice from this integral is that the integration bounds are not -1 to 1. And so we need to perform our change of coordinates. Okay. And to do that, we need our function x of epsilon. Okay. Now, so we know that this is equal to x1 n1 plus x2 n2. Okay. For n1, n2, these are functions of epsilon. Okay. And so let's go ahead and plug in for this problem. For this problem, we have x1 is equal to 0, x2 is equal to 5. Okay. And so we have 0 times n1 of epsilon. So we scroll back up here. We can see that n1 of epsilon is 1/2 multiplied by 1 minus epsilon. Okay. So we have 0 times 1/2, 1 minus epsilon, plus 5 times 1/2, 1 plus epsilon. Okay. All right. And so you can see the first term here is going to go away because we have a 0. And then what we're left with is 5 divided by 2 times 1 plus epsilon. So not the cleanest X in the world, but it's you know, it'll do. All right, so the next thing we need is our Jacobian, of course. And so our Jacobian here is dx d epsilon, which is simply x2 minus x1 divided by 2. Okay. Or you can just take the expression we have up there and take the derivative, whichever is easier. You get 5/2. And once again, you see it's a ratio. And so our original integration domain had a length of 5. Our new integration domain has a length of 2. And so this is just simply a ratio between those two quantities. Okay. Okay, so now let's go ahead and plug in. And so, you know, to perform our change of coordinates, right, we started out with this integral here. So we have 200 integral from 0 to 5 of 1 plus x squared divided by 400 dx. Okay. And so we're going to go ahead and plug in for this. Okay. And so to plug in, we're going to do a few things. And so first, And so first of all, which is the whole point of the change of coordinates, we're going to change our integration bounds to -1 to 1. Okay. Next thing you're going to do is that everywhere that you see x in your integrand, you're going to plug in x of epsilon. Okay. And so that means, yes, that means we're going to plug in this entire function right here. Right. Everywhere we see x, and so it's going to be a little bit messy, I know, but that's how we're going to do it. Okay. And then 3, we need to multiply by the Jacobian. It's going to look a little bit messy, but remember, we're not actually integrating this. We're applying Gauss Quadrature. That's the whole point. Right? Okay, so let's go ahead and apply this. And so we have an integral from -1 to 1. Right? Then our function here is a 1 plus, we have an x squared here. And so instead of x squared, we're going to plug in 5 over 2, 1 plus epsilon. Okay. This whole quantity is going to be squared. We're going to divide by 400. Okay. We're going to multiply this by our Jacobian, which is 5 over 2. And we're now going to be integrating by d epsilon. Okay. So I think the thing that trips people up the most is that we're no longer integrating in x, we're integrating in epsilon. And so whenever you see x, you have to plug in our function x of epsilon. Okay. It does make things a little bit messy, but the whole point of the change of coordinates is to kind of get rid of x as much as possible. Okay. And so by plugging in this function x of epsilon, we effectively get rid of x and we transform it to its equivalent in epsilon. All right. Any questions on how we obtain this? Okay. All right. And so now that we have the integral in this form right here, we can go ahead and apply our 2-point Gauss rule. Okay. Okay. And so remember, our 2-point Gauss rule, we have two points, right? And so point one has a weight of 1. Okay. And the location for that is going to be a -1 divided by √3. Okay. Point two also has a weight of 1. And we're going to evaluate our integrand here at a +1 over √3. Okay, and so if we apply that integral, well, first thing I'm going to do is, because we have this 5/2 here, I'm going to go ahead and pull that out. And so we have a 200 times 5 over 2. And so that's just going to be 500. Okay. And then first we have our integrand applied at our first Gauss point. And so at our first Gauss point, we have a 1 plus, go ahead, put parentheses around this, 1 plus 5 over 2 times 1 minus 1 over √3. Okay. 180 squared divided by 400. Okay. And so this right here is our integrand evaluated at the first Gauss point. Okay. And then to that, we're going to evaluate the integrand at our second Gauss point. And so at the second Gauss point, we have a 1 plus 5 over 2 times 1 plus 1 over √3 squared divided by 400. Okay. And this right here is our integrand evaluated at second Gauss point. Okay. And so of course, this is kind of a pain to evaluate by hand. And so you would use a calculator. But again, this is another one of those things where this is designed to be a computer algorithm, right? And so the thing that computers are really great at over humans is that they can take, an expression like this, which has a lot of arithmetic in order to evaluate, and they can evaluate it just like that. Okay. And so we're going to start it today. And so what you'll see is that, we're going to program this Gauss Quadrature directly into MATLAB and have MATLAB kind of do a lot of the heavy lifting. And so the only thing we have to do is just, kind of set it up for MATLAB to do it. Okay. But if you actually ran through these calculations, and so I did do that for you. Okay. And so if you, plug this into a calculator or something, you get a result of 1020.83. Okay. And if you go back to the start of the problem, that's exactly what our answer was. Okay. And so with the 2-point Gauss rule, we were able to approximate this integral exactly. Yeah. Say again. Yeah. So these are the predefined Gauss points. And so if we go back to our notes from the last time, this is just how it's defined. And so yeah. So the proof for this is very, very long, but these points are kind of what maximize the accuracy as much as possible. So, yeah. And so there's different locations for a 1 point, a 2 point, a 3 point, and there's even more points than that. Yeah. But usually you won't need more than 2 points. 2 points is already really good. And then that's you can get a pretty good answer from that. Actually, if you're curious, so I mentioned that Gauss Quadrature gives you great convergence criteria. It works especially well for polynomials. And so when you have polynomials, Gauss Quadrature, there's nothing really that beats it. Okay. And so the rule for polynomials for polynomial integrands, the rule is that if you use Gauss Quadrature with n number of points, if you use Gauss Quadrature with n number of points, you are guaranteed to approximate the integral exactly for a polynomial of order n. Okay. And so whatever order your polynomial is, you only need Gauss Quadrature points up until that order. Okay. I actually think it's n+1, but it's been a while since I've looked at the proof. So and so I'm just going to say n. And so for n for sure, you're going to get an exact one, right? We just proved it here, right? And so we have basically a second order polynomial. We have x squared. We use a 2-point Gauss rule, and then we got an exact solution. And so I think this is actually n+1, but I'm not 100% sure on that. I need to look back at the proof again. I'm kind of just ad-libbing this as we go. But I know at least if it's n, you're guaranteed to do that. And that's another reason why it's used a lot for finite elements, because in finite elements you get a lot of integrals that involve polynomials, and so it just very, very naturally kind of approximates that really, really well. All right, any questions on this? Okay. And so actually, before we do go to the MATLAB implementation, I do want to talk very briefly about quadratic elements. Okay. We're not going to see it that much in this class, and you'll see why very quickly. but it is an option in ANSYS, right? And so in ANSYS, you have an option when you make your mesh to make quadratic elements. And in fact, if you're coming from 540 last semester, or if you remember from the last two activities, I actually always tell you to do quadratic elements for for structural problems. So let's go ahead and talk about what that means mathematically for our shape functions and our element stiffness matrices and things like that. Okay. And so, you can probably guess by this point, but, when we say that our element is quadratic, what that means is that our shape functions have quadratic polynomial order. Okay. Okay. And so for our linear function looks something like this, right? And so our linear element only had two constants to solve for. So we had the constant, as well as the coefficient for the linear term. Okay. For quadratic, we have one additional term here. Okay. And so our shape functions are going to look like that. Right? And so we have one extra constant to solve, one extra coefficient. Okay. And if you remember, when we solve for these coefficients in the linear sense, the way that we solved for them was that we enforced. Okay, and so here's our element, right? Oops. Right, and so in order to solve for these constants, right, what we enforced was that our interpolation function has to match the nodal solutions. Okay. And so in a sense, you can basically think of it as, we're enforcing two Dirichlet boundary conditions. So we say that at x1, the solution has to equal T1, and at x2, the solution has to equal T2. Okay. And so for two nodes, we got two conditions, and for those two conditions, we solve for two constants. Right? But we have a problem with quadratic elements. And so for quadratic elements, we have a third coefficient, right? And so for quadratic elements, that means we need one extra condition in order to solve for it. Okay. And so that kind of implies that we need an extra node, right? But we can't put another node in the middle of these, at the ends of these elements. That's already taken. And so we're going to put a node in a location where no node is currently there. Okay. And so we're going to put that node right in the middle of the element. Okay. So we'll call this node 3. And then we're going to enforce our solution to match our solution at node 3 right there. Okay. And so whenever you add a node in the middle of an element here, it's a little bit tempting to say that, okay, now that we've added this node, instead of one element, we have two, right? And so we have an element that goes from T1 to T3, another element that goes from T3 to T2, right? It's tempting to say that, but that's not the case. And so even though we have 3 nodes here, these 3 nodes comprise just a single element. Okay, so this is still just one element. It's just that now we have 3 nodes into it. Okay. And since we put this node in the middle, it has a very special name. And so we call these nodes, we call them mid nodes. Okay. Okay. And so it's all still part of the same element, but we just have one extra node. Okay. And with that extra node, we're able to solve for all three of our constants. Okay. And so if you ever feel like you want to suffer, and maybe you played Elden Ring recently, and that's not enough suffering for you, you can go through this system right here and actually solve for all 3. It's not fun. I've never personally done it myself because I'm not that big a masochist, but people have done it. And so I'll give you the solution, but it's a you'll see very quickly why no one wants to do this. Okay. Okay. And so take note that these are quadratic functions. Okay. And we now have 3 shape functions now too, because we have 3 nodes, and so that's going to give us 3 shape functions. Okay. And so we have n1 of x, okay, is equal to x minus x2 times x minus x3, all divided by x1 minus x2, multiplied by x1 minus x3. Okay. And 2 of x is equal to x minus x1, x minus x3, all divided by x2 minus x1 and x2 minus x3. And finally, we have n3 of x is equal to x minus x1, x minus x2, okay, multiplied by x3 minus x1, x3 minus x2. And so the solutions are elegant, and so they follow kind of a nice pattern, and so they kind of a nice cadence to them. But obtaining this is not fun. And so you're talking about a three equation system with 3 unknowns, but it's all symbols, and so it is the definition of mathematical algebraic pain. And so but that's the result. All right. So what's the upshot? So why am I sharing this with you? And so what you'll notice and what you'll see is that quadratic elements always have more nodes than linear elements. Okay? And you could test this out very easily too. So if you take the last ANSYS activity and you mesh it using linear elements, you can use the mesh statistics to see how many nodes that you have. Then without changing anything else, change the element to quadratic and see how many nodes you get, and you'll see the quadratic mesh will have more nodes no matter what. Okay. And the reason for that is because we have to include these mid nodes in order to solve for these expressions for the shape functions. Okay. And another note, and I'll just talk about this one, is that when you actually use these shape functions and you plug them into the weak form, right? So another weak form of that's how we obtain our element stiffness matrix. Instead of getting a 2x2 element stiffness matrix for our linear elements, for our quadratic elements, we're going to have a 3x3 element stiffness matrix. And so, those also are going to require a bit more work. Right. Any questions on any of this? Okay, all right, so we have about 20 minutes left in the class, and so I do want to start the next set of lecture notes, which have to do with the MATLAB implementation. And so we'll start it today, and then we'll continue it on Wednesday. Okay. And so the format of this of these lecture notes is kind of takes the same form as the last time we did MATLAB. And so what I have is a PowerPoint presentation, which kind of walks you through the logic, and I've posted a starter code as well. Okay. And so if you look at the starter code, there's a lot of to-do segments. And just like last time, we're going to fill in those to-do segments as we go along with the lecture. And so I don't think we're going to get too much into the meat and potatoes of this. And so I think we're just going to introduce the code. And so for today, you can probably just kind of chill out. But on Wednesday, we'll start actually filling in this code in earnest. Okay? And if you want to download everything, you come here to the course website, you go to week 11, and you can see here that I posted this code right here for finite element 1D BVP start. Okay? And so you download that code and you're going to get the same code that I have up here. Okay, so let me go ahead and move on to the slides, and we'll kind of talk our way through this until the end of the class. Okay, and so the title of this is to implement a 1D boundary value problem in MATLAB. And so kind of the exact same finite element problem that we covered at the end of lecture before the spring break. We're going to learn how to implement that in MATLAB using Gauss Quadrature and automating a lot of the mathematical processes. Okay. And so this is going to be another code. I will say that it's a lot shorter than the truss code and the frame code. And so those were kind of a little bit of a trial by fire. And so these codes will be a lot shorter, but a lot of the same structure and a lot of the same logic that we developed in those codes, we're going to use here as well. Okay. And one nice thing that we're going to have here for the 1D codes is that we can actually plot our results. And plotting is great because it kind of very quickly allows you to kind of visualize, what your solution looks like and how close you are to the exact one. Okay. And so throughout this tutorial, we're going to work on the following problem. So we have a 1D heat transfer problem, 1D heat conduction. And so what we have here is a rod that is fixed to a wall, and the wall is being held at a fixed temperature, right? And so I believe the fixed temperature, yes, the fixed temperature here is 25 degrees C. Okay. The length of the rod is going to be 5. Okay. We have a Neumann boundary condition on the other side. Okay, so we have a heat flux here. And so you can think of this as a load. And so the heat flux on the other side is going to be 600 watts per meter square. Okay. We have the thermal conductivity. So the thermal conductivity here is a constant. And so we have a constant thermal conductivity of 50. Okay. Our area is going to be a constant as well. So our area is going to be 0.1 meters squared. Okay. So that's going to be nice because then that simplifies our element stiffness matrix quite a bit. Okay. And then we're also going to throw in some thermal generation as well. And so our thermal generation is going to have the functional form of x squared. Okay. And so you can take these parameters here and you can solve the strong form of the equation. And so if you solve for the strong form, okay, and so if you solve for the solution to the strong form, you get the following function. And so you get minus 1 over 60 x to the 4th plus 61 over 5x plus 25. Okay? And so if you want, you can solve the strong form and verify that, but I've already kind of done that for you. So this code here, we're going to focus on just the finite element solution. All right, any questions on this? On the problem setup? So one of the nice things about this, and I think what makes it a nice introductory code, is that the K and the A here are constants, right? And so the homework problem from this, after all this is done, I'll go ahead and skip to the end. Oops, did not do what I wanted to do. Right. So for the homework, you're going to do the same problem, except now your area and or excuse me. So the area is going to be vary with x, and your thermal generation function is going to be a bit more of a complicated function here. Okay. And so that's kind of what we're kind of building up to. So that's kind of something to keep in mind. Okay, so let's go ahead and start implementing the code. And so let me go ahead and open up the code here. Okay. Right. And so you can see I split this code up into several different sections, just like I did before. Okay. And we're going to go through each section here and then kind of define what each of them do. Okay. All right, so the first one, the first section of the code is we're just going to define problem parameters. And so just like the last one. And so all of the kind of physical parameters that the problem has, we're going to define up here. Okay. All right, so these are all fairly straightforward. And so we can go ahead and define these just based off the problem statement. So let me go ahead and bring up the problem statement here. Okay. First thing we're going to plug in for is the length of the domain. And so the length of the domain here is 5 meters. And so let's go ahead and plug in 5 for this. Okay. Oops. Our thermal conductivity here is 50, and so I'm going to plug in 50 for this. Okay. Okay. Our area here is 0.1 meters squared, and so I'm going to plug in 0.1. Our T naught here is our Dirichlet boundary condition on the left-hand side, and so this is equal to 25. Okay. Next, we have our heat flux boundary condition. And so we have our heat flux boundary condition, Q out. Okay, so this is 600 watts per meter squared. And then finally, we define the number of elements. And so the number of elements here, this is something new. And so in the previous code, the number of elements that we had in our truss or a frame was more or less fixed, right? And so that was kind of determined by the problem. Here, what we're going to be doing is we're going to take our domain here and kind of break it up into elements, right? And so the way I'm kind of designing this code is that, we're going to design it as kind of a general code. And so you can kind of change the number of elements on the fly. Right? And so this code is going to automatically adapt itself for 4 elements or 40 elements or even 400 elements, okay? But to start out with, let's start out with something simple, just so that we can kind of verify the results. And we'll start out with 5 as the number of elements. Okay, and so we're going to break up this domain here into 5 elements, and then solve for the solutions on those 5 elements. Okay. Any questions on this so far? Okay. All right. So let's go ahead and move on. And so this slide here, we've already kind of done it. Okay, and so the next thing that you'll see that's missing is our connectivity matrix, right? And so if you remember from our previous code, we had this data structure inside the code called connectivity, right? And so what that connectivity matrix defined was, if you have a certain element and you have an ID number for that element, the connectivity matrix told you which nodes were connected to that element, right? Because when you're doing finite element problems, you have to keep track of, each of the elements in your mesh, and you have to keep track of all the nodes in your mesh as well. And we usually give ID numbers to each of those. And so we did that in the previous one, and we kind of forced it to happen with the connectivity. But for 1D problems, we don't really have to worry about that because each of the nodes here are going to be listed kind of sequentially to each other. And so we start with 1 on the left-hand side, we go all the way up to 12 on the right. And the same thing for the elements. So for the elements here, we're going to start with element 1 here on the left, and then we're going to go all the way up until the maximum here on the right. Okay? And so if you look at any particular element, okay, so let's look at element 3 as an example here. It's very easy to tell, which nodes are connected to that element. And so the left element, or the left node, excuse me, the left node here has the same ID number as the element. Okay, and so element 3. Its left node is going to be 3, and its rightmost node is going to be the ID number of the element plus 1. Okay? And so if you wanted to define a connectivity matrix, you could, but for this one, it's kind of trivial. And so we have node 1 is equal to I, where I is the ID number of the element. Okay, and node 2 is equal to I plus 1, which is 1 past that. And if you look at any element here, it kind of follows that same pattern. Okay. And so here it's kind of unnecessary for us to define a connectivity matrix just because we kind of already know what the connectivity looks like in 1D problems. Okay. And so I'm explicitly listing this. And so, it may kind of seem obvious for a 1D problem, but once we start going back to 2D, the connectivity matrix is going to be important again. So I don't want you to forget about it. But for this one, it's kind of unnecessary just because it's a little bit trivial. All right. Any questions on this? Okay. All right. So next we have data containers, and so just like the previous code, we need to create data containers for the global stiffness matrix, the global forcing vector, and also the element stiffness matrix. Okay. But unlike our previous codes, or unlike the frame and truss problems, we have to account for body forces or thermal generation as well. Okay, and so we have one new data container here, which is F element. Okay, and so F element is going to be our data container for our element forcing vectors. Okay. And so not only do we need to save the element stiffness matrices, but we also need to store the element forcing vectors as well. Okay. And so that's what F element there is meant to represent. All right. And so, one question that I have here is that, look at the sizes of each of these data structures, right? And so for our global stiffness matrix, we have n elements plus 1 by n elements plus 1. Okay. Where, remember, the first entry here, this is the number of rows in the matrix. And this here is the number of columns. Okay. And so there's the fact that, our global stiffness matrix is n element by n element, or excuse me, n plus 1 by n plus 1. Does that make sense to you, right? And so if we go back to the previous slide, you can see here we have, in this particular image, we have an 11 element mesh, right? And for 11 elements, we have 12 nodes. Okay? And so if we're going to solve for the solution at those 12 nodes, then our global stiffness system should be 12 by 12, right? So we should have one row, one equation for each node in our mesh. Okay? And for a 1D case like this, the number of nodes that we have is always going to be a number of elements plus 1, right? And so if we have 11 elements, we're going to have 12 nodes. If we have 50 elements, we're going to have 51 nodes, right? And so it makes sense that this should be a n plus 1 by n plus 1 matrix, just so that every element, or excuse me, every node in our mesh will have a row accounted for it in the global stiffness system. Okay? Same thing for F global. So for F global, it's a vector, right? And so it's not a matrix. And so the number of entries in that vector should be n plus 1, right? So n number of elements plus 1. And then finally, let's look at the size of K element and F element, right? So the most relevant numbers for this are the first two, okay? Because remember, we're storing every single element stiffness matrix so that we can assemble them later, right? But each element stiffness matrix themselves is going to be 2 by 2, right? And so you can kind of see right away that we're going to be assuming a linear interpolation function. And so for linear shape functions, then our element stiffness matrix is 2 by 2 for a 1D case. Okay, and then our element forcing vector also only has 2 entries. Because for each element we only have two nodes. Okay. Okay. Any questions on this? Okay. Okay. And so next we have a section that we need to fill in. Okay. And so the next thing that we need to fill in is the nodal coordinate vector. Okay. And so what this does is that it tracks the x positions for every node in our element mesh. Okay. And so if I go back to this figure right here, what the position vector is going to track is, we have x1 here, x2, x3, right? And so each of these nodes, they each have a physical coordinate that denotes kind of where it's located in space. Okay, and so we need to keep track of that because that's going to be important for us to, for us to solve our system. Okay. Okay, and so we can create this vector, with one line of code, and the line of code that we're going to use is called Linspace. Okay, and Linspace takes 3 different arguments, and so Linspace first takes the starting x coordinate, it takes the ending x coordinate, and then it asks you for the number of points that you want. Okay. All right. And so what this does then is that it creates a vector where, the first entry will be x start, the last entry will be x end, and then everything in between will be equally spaced to each other. Okay. All right, so let's go ahead and fill that in. All right, so we have pos vector here, and so for pos vector, we're going to use the function Linspace. Okay. And so let's look at the starting x coordinate. Okay, so let me go back up to the figure here. Okay. All right. And so you can see here that the starting x coordinate here, we're going to assume that the left-hand side of the wall has an x coordinate of 0. And so x start here, we're going to say 0. Okay. Meanwhile, the location of the rightmost or the ending part of this domain here is going to have a location of 5, right? Because that's the length of the domain. Okay. But we can do a little bit better than just 5, right? Because what if we want to change the length of this domain? So, let's say that instead of 5, we want to solve it for a length of 3, right? And so if we do that, we have to change this value here to 3 as well, right? Okay. But we don't have to do that. And so we've already defined this variable L to represent the length of the rod. Right, so let's go ahead and use that here for the Linspace. Okay, and so we can say that the ending x coordinate here is going to be L. Okay, and the number of points that we need is going to be the number of elements. Okay, but remember, these are the positions of the nodes, and so we don't want the number of elements. We want number of elements plus 1, right? Because that's the number of nodes that we have. Okay. Right, and so we're basically making the assumption that each of these elements are kind of equally spaced. So even though it's possible, and I think we did an in-class example of this, of where the elements are different sizes. For here we're going to assume that all the elements are the same size, just kind of for the sake of simplicity. Okay. Any questions on this? Okay. All right, so that's pos vector. And so the next thing that we're going to compute here is the length of the element. Okay. And so the length of the element, you can compute this in quite a few different ways, actually. Okay. And so the simplest way is to say that, the length of our domain is L, right? And we're going to split that L into, an element, number of elements. Okay. And so what you can do is you can say that L element here is equal to a big L divided by n ln. And so that's going to take take the length of your domain divided by the number of elements, and that's going to give you the length of each individual element, which we're going to assume is all the same. Okay? And so that's probably the simplest way to compute this. Okay? Another thing that you can do is you can take your pos vector here, okay? Because this already has kind of spaced everything together, equally. And so what you can do is you can take the difference between the first two entries in pos vector. And so you can take pos vector 2 minus pos vector 1, right? And that'll give you, the length of each element as well. Okay? Because the difference in distance between the first node and the second node is going to be the same as the distance between the second and third node, same as the third and the fourth node, and so on and so forth. Right? And so that's another way to compute the length of the element. But for me, for a simple case like this, I just do L divided by n. Okay. All right. Any questions on any of this? All right, so the next step in the code is to compute the element stiffness matrix, but that I don't want to start that yet because that we kind of should do all that together, and we only have 2 minutes left today. So we'll call it here. Okay. And so thank you everyone for tuning in today. Hope you guys enjoy the rest of your evening, and I'll see you on Wednesday for us to finish up this code. Thanks, Tristan. So for the homework, this problem at the end right here, this is going to be part of the next homework. And so for this homework that you're turning in next Monday, I just want you to focus on the hand calculations. And so, you don't have to worry about for the MATLAB, but then for the next homework after that, I believe it's part of ANSYS activity 3, actually. Then you're going to implement that code. Yeah, but for this homework assignment, just do the hand calculation. There's no MATLAB for this at all. Yeah. Thanks, guys. Have a good night. Yeah, and so even though the answer is T1 to T5, you can compute that by hand as well. You might need to use MATLAB to solve the linear system, and so you just like we did with direct stiffness. Once you get the linear system of 5 equations, 5 unknowns, you can solve that in MATLAB, but you don't have to use this code to solve it. And so this code is something separate, and so this code is kind of an automatic solver. But you can solve all these problems. I want you to work them through by hand, get the matrices by hand, and then once you solve for and once you get to the matrix, you can solve for that in MATLAB. Yeah, we went over this. We went over how to do these problems kind of right before the spring break. And so if you need reference for that, you can check out. I think it's lecture notes 08. And then the lecture from lecture 2 from week 9 will go over that method as well. Yep. Angel, any final questions?